When you see those incredible, mind-blowing images from an electron microscope, have you ever stopped to think about what's really going on in there? We see the results, right? But behind it all is a single particle, the electron, and it's living a life that follows some of the absolute strangest, most wonderful rules in the entire universe. So let's pull back the curtain on that. It really all boils down to this question. How on earth can we see the literal building blocks of matter? The answer, it turns out, isn't just about making things bigger. Nope. It's about wrangling the very peculiar secret life of the electron, a particle that is somehow fast, lonely, uncertain, and impossibly focused, all at the same time. So here's our roadmap. We're going to explore these 4 chapters of the electron's life inside a transmission electron microscope. And we're starting with its frankly ridiculous speed. And when I say fast, I really mean it. We're not talking fastball fast or even jet fighter fast. We are talking about a speed that is a huge chunk of the ultimate speed limit of the universe itself. That's right, over 77% of the speed of light. At that kind of velocity, the bizarre world of Einstein's special relativity, well, it isn't just some abstract theory. For our little electron, it's just another Tuesday. It's the daily reality inside that machine. And this is where things get, well, weird. This is where we compare our time to the electron's time. From our perspective, standing here in the lab, the electron is just moving incredibly fast. But from the electron's point of view, time itself is slowing down for it. It feels like it travels over 1.2 light years in what it experiences as just 1 year. That is real-world time dilation happening right inside a piece of lab equipment. Wild. Okay, so for our next chapter, I want you to just completely forget any idea you have of a dense beam, like a flood of electrons, all crashing into a sample. The truth is much, much stranger and way more solitary. The secret is the spacing. On average, any given electron is separated from the next one by almost 4 centimeters. Now, that might not sound like a lot to us, but for a tiny particle like an electron, that's a colossal empty void. And that simple fact leads to a conclusion that is absolutely mind-bending. Yep, you saw that right. For a huge portion of the time the microscope is running, there's only a single, solitary electron flying through the entire instrument. So, hold on. If they aren't interacting with each other, how in the world do they create those beautiful, complex patterns we see? And the answer is just peak quantum mechanics. It's called self-interference. See, the electron isn't just a tiny ball. It also behaves like a wave. This one lonely electron wave travels through the sample, it takes multiple paths at the same time, and then it literally interferes with itself on the other side. That's how the image is built, one single lonely electron at a time. It's just incredible. All right, next up is a quality that seems like it should be a bad thing. In the quantum realm, sometimes not knowing something with perfect precision is actually a massive advantage. And it's all thanks to the famous Heisenberg uncertainty principle. Now, this isn't a limitation of our tools or our measuring ability. It's a fundamental property of the universe. You simply cannot know both exactly where a particle is and exactly where it's going at the same time. But here's the clever part. Scientists can exploit this. They can actually choose what to be uncertain about to get the image they want. And I just love this analogy of fat versus long electrons. So for the fat electron, scientists get super precise control over its angle, its momentum. The trade-off? Its side-to-side position gets really fuzzy and spread out, which turns out to be perfect for advanced techniques like holography. Then you have the long electron. Here, they lock down its energy with incredible precision. The trade-off this time? Its front-to-back position gets all stretched out and uncertain. And that stretching is exactly what helps kill image blur, giving us those razor-sharp pictures. And that brings us to our final and maybe the most jaw-dropping property of all. We all kind of know what focus is from taking photos, right? But the focus in an electron microscope, it just operates on a level that completely breaks our everyday intuition. So, with a normal light microscope, you focus on one thin layer at a time. A bug's feet are sharp, its antennae are blurry. A scanning electron microscope, an SEM, is way better. It gives us those famous, slightly terrifying close-ups of insects where the whole thing is sharp. But a transmission electron microscope, a TEM, takes this to a level that is almost unbelievable. Just let that sink in for a second. That is not a typo. The depth of focus is so staggeringly huge that the image would still be sharp even if you moved the camera film or the detector a kilometer away. It's basically perfectly focused over an insane distance. So you see, none of these things work alone. That perfect atomic scale image is a masterpiece created by the teamwork of these four properties. You need the fast electron to get the power from relativity. You need the lonely electron for quantum interference. You need the uncertain electron for clarity. And you need that ridiculously focused electron for that incredible depth. It's this beautiful dance between relativity, quantum mechanics, and optics. And that leaves us with this final thought. A challenge, really, from the person who wrote the article this is all based on. We've seen that all these things are true, but why? Why is the focus so impossibly deep? It's a fantastic question that just pushes us to look even deeper into the secret life of the electron. And it's a great reminder that even inside our most advanced machines, there are always more wonders waiting to be discovered.